The concept of power. Power has two closely related definitions. Power is the rate at which a force does work, and it's also the rate at which a process transfers or transforms energy. So we'll discuss both of these meanings, focusing on this first. The average power output by a force doing work is defined as the amount of work done divided by the amount of time that it took. Looking at our units, we have Newton meters of work divided by seconds in time in SI units. A Newton meter we know is the same thing as a joule of energy. So this is joules per second. And 1 joule per second in the SI system is defined as 1 watt of power output. So that's capital W for watts, the SI unit for power. Now, unfortunately, we're already using capital W to represent work right here, and yet capital W is also the abbreviation for the unit of power, watts. So there's a bit of a notation hazard. For my part, I will always write a capital W for work like this, but a capital W for watts, I'll put little serifs on it there to distinguish it from the W for work. Uh, Average power output by a constant force doing work over time, can be found by using this formula for work divided by time, or formula number 2 for work divided by time, work done by a constant force. So let's simplify these two formulas to get another expression for average power. Here we see delta R over delta T. Well, that's going to be the magnitude of the average velocity. So magnitude of average force, or magnitude of that constant force, times the magnitude of the average velocity of the object times the cosine of theta, theta being the angle between the constant force and average velocity or displacement. That represents the average power, the average rate of doing work. Force times velocity gives us power. Or using a formula 2 for work, delta x over delta t, that's going to be the x component of average velocity, and delta y over delta t, that's the y component of average velocity. So we can also find average power by a constant force doing work by taking fx times v average x plus fy times v average y, the sum of the products of the parallel parts. If we want the average power output by a constant net force doing work, so this could be average power from one single force, force times velocity, force times velocity. But if we look at the net force on the object, and if that is constant, then net work divided by time, well, according to work energy theorem here, net work is the same as kinetic energy change, delta K. So net work over time is delta K over delta T. And we see that the average power output by a constant net force gives us the rate of transfer of kinetic energy, how rapidly you're adding or removing kinetic energy from the system. So energy over time, once again, 1 joule per second equals 1 watt. Energy over time is power. One more formula here. The two previous formulas are for average power over some time interval. If instead we want the instantaneous power output by a force doing work at one particular moment, we can get that with a very similar formula. At one instant, the rate at which that force is adding or removing energy is given by the magnitude of the force at that instant times the speed at that instant times the cosine of the angle between the force and velocity vectors at that instant. Or fx vx plus fy vy, the sum of the products of the parallel parts. Either of these gives you the instantaneous power. And this formula applies at any one moment, even when the force and the velocity are varying with time. So this formula is good from moment to moment, even when force is not constant. Note that we assumed constant force and constant net force for these two formulas here. All right, so with those formulas in place, let's look at a scenario here. We have two cranes competing with each other to lift an identical load. Both cranes start out with the same amount of chemical potential energy. So this is their fuel, the fuel in the engine that's powering the crane here, or the fuel in the muscles of the person or animal that's going to be cranking the crane. So at time zero, both bins are at rest. What's going to be happening is that the normal force on the bin from the platform is going to be doing positive work, transferring chemical potential energy from the engine into kinetic energy for the bin. We're going to be lifting at constant velocity. So that means we're not building up kinetic energy over time, because the force of gravity here is going to be doing negative work to match the positive work being done by the normal force, converting that kinetic energy into gravitational potential energy as the box gets higher and higher. The difference between the two cranes is that this crane on the right is going to have a greater power output. It's going to do the same amount of work as the first crane, but in less time. So here's the situation at time zero. Here, 1 second later, both cranes are working, both loads are moving, but this one is lower than this one because this one is moving upwards at a greater constant speed. Suppose they're both moving at a constant speed, but this is a greater constant speed, so it's gone farther in 1 second. Then by the time we get to 2 seconds, this crane has gotten the load already to the top. This one is still moving. So in the middle here, you can see that on the right, this more powerful crane has transformed this much chemical potential energy into green gravitational potential energy. This crane has only transformed this much chemical potential energy into green gravitational potential energy. It's going to take the crane on the left 1 additional second to get to the top. So by the end, both bins got to the same place. The same amount of work was done by both cranes. They used the same amount of fuel to add the same amount of gravitational potential energy to identical bins. This crane just did it in less time. So here's our final energy scenario. All that gravitational potential energy was shifted through the positive work done by normal force and the negative work done by gravity into gravitational potential energy. The amount of work done we can find from this formula, Fy delta y. So if we have a 10 kilogram mass here, so mg is going to be 10 times 9.8, that's 98. That's about 100 newtons Fy times the displacement of 12 meters. So 1,200 Newton meters of work was done by both cranes. The same work was done, but in different amounts of time. So the cranes had different power outputs. So here's where the power comes into play. The average power output from each crane is the work that crane did divided by the amount of time that it took. So this crane on the left did 1,200 Newton meters of work in 3 seconds. That's 400 watts. A 400 watt engine powers this crane here. 400 watts is equivalent to about 0.54 horsepower, a unit I'll discuss another time. This crane, however, on the right, did that same amount of work in only 2 seconds. So it had a power output of 600 watts. 600 watt engine here versus a 400 watt engine here. They can do the same work. This will do it in less time. 600 watts is equivalent to about 0.8 horsepower. I computed the work here and here using work over time, but we could also have used this formula here, force y component times v average y component. Let's try that formula as an alternate way to get this same result. So same scenario, using the alternative but equivalent formula, let's find the average speed of the bins in each case. So in each case, the bins moved upward 12 meters. This bin took 3 seconds to do it, so it had an average Vy of 4 meters per second. This bin took 2 seconds to do it, so it had an average Vy of 6 meters per second. So different average speeds, but they were lifted with the same average force of about 100 newtons, the weight of the bin. Same average force because that force just needed to match the downward force of gravity in order to lift the bins at constant speed. So both cranes have the same tension in the cable to exert the same force. They just lifted at different average speeds. So this crane, 100 newtons times The low speed of 4 meters per second did 400 watts, or had a power output of 400 watts. This crane, same tension, but at a higher average speed, 600 watts, reproducing the result we got from the other formula.